Okay, I'd like to get this today's seminar series started, and I'm really pleased to introduce to you Samantha Blair. Samantha is actually an astrobiologist, that is, a multidisciplinary scientist who's taken seriously the studying of many different fields. Some of us just play at it, but Samantha's the real deal. She actually has a BS in forestry from Auburn University, and then an MS in plant molecular biology. And after that, she did some field work in marine science, looking at anaerobic methane oxidation in marine sediments, and then went on to the University of Georgia to get her PhD by becoming a radio astronomer, to actually look at formaldehyde and HCN in the outer galaxy and start to help piece together the whole story about how the chemical building blocks for life ended up on this planet and in us. And today she's going to tell us about work that she's been doing with Dave Messerschmidt, Jerry Harp, and myself on trying to combine communications theory and our knowledge of interstellar medium to see if we can figure out if there's a particular class of high-dimensional wideband signals we should be expanding our search to include. So thank you, Samantha.
Thank you, Jill.
Good to have you here.
I've got a
You've got
this thing on. Okay, so with that introduction by Jill, I was looking at this title last night, The Effects of the Interstellar Medium on Signals of Extraterrestrial Origin, by myself in collaboration with and under the supervision of David Messerschmidt, Jill Tarter, and Jerry Harp. And I looked at the title and I thought, well, what did I know about this last year when I got here? And the only two words I knew about were interstellar medium, and the only things I knew about the interstellar medium were that there are molecules out there in giant molecular clouds. And so since I've been here, I've actually been working in interstellar medium physics, so that's the effects of this, on signals. That's communication theory and digital signals processing and the extraterrestrial origin. So that's what I'm going to talk about today, is the work I've been doing on this. So what I'm going to talk about is justification for a new SETI search. Why are we looking for these new types of signals? I'm going to talk briefly about the interstellar medium. The effects we're going to look at are dispersion and scattering. In order to understand these effects, we have to model them. So I'm going to talk about modeling of the ionized interstellar medium. I'm going to show some modeling results, talk about how we can apply this to broadband signals, and then I'll have some conclusions. So in order to detect a signal, you look at detection sensitivity in the presence of white noise. And this depends on knowledge of the signal waveform. So sometimes you need to make assumptions about this. Typical assumptions that have been made are that it's a sinusoid, a pulse, etc. In terms of sinusoids, they really have little effect by the ISM. They can transfer through the ISM fairly easily without much aberration. The Cyclops, Project Cyclops in the 1960s basically gave this prescription to look for sinusoids. And as you see here, this is a waterfall plot, and the signal that you would detect would be that line, frequency versus time, on the axes. But the narrowband search, I mean, it's very logical. It's still going on now. I have a diagram over here that's showing a narrowband waveform versus a spread waveform. And with narrowband, it's usually 10 hertz or less. So that's what we're calling narrowband. These are not found in nature. There are some narrowband emitters, like masers. But the typical line widths of like spectral lines I would see in H2CO or HCN, 3 kilometers per second, which is 15 kilohertz or so, and that's kilohertz. And those lines look narrow to me, but they're not compared to the lines that they're looking for. So if you find one of these narrowband waveforms and you eliminate it from terrestrial interference, then it could be of technological origin. So very sound reasoning for a search. But looking at a modern radio, does that tell us anything about potential interstellar communication? So on the left-hand side here, we have the analog system that was used, carrier modulated with minimal bandwidth. Modern advances have developed spread spectrum technology, digital, and has actually more bandwidth. So spread spectrum may be the way to go to look for new signals. It's pretty much ubiquitous in multi-user wireless and Wi-Fi and some cell phone communications. It uses far more bandwidth than necessary. And this signal waveform you see here is a typical noise-like signal. It has some advantages that apply to interstellar communications. It's fairly robust against interference, robust meaning rejection of interference, and it doesn't matter what kind of interference we're actually talking about. And also it has some advantages in terms of multipath effects. It's not so affected by multipath issues. So talking about interference, obviously it's a growing issue for SETI because of all the signals that are being sent out on this planet. So you can make the claim that immunity is robust if and only if the signal is white noise-like. This provides a design-based transmitter-receiver coordination of signal choice. And immunity is proportional to the time bandwidth product. And luckily, in interstellar space, bandwidth is ample. Time is not necessarily so readily available. So here's an example of a noise-like signal. And if you look at this diagram here in time, it's immune to a pulse-like interference. So if you insert a narrow pulse in here anywhere, it's really not going to have that much of an effect. If you look at frequency, it's immune to carrier-like interference. If you have a narrowband carrier and you insert it anywhere in here, it's not going to have that great of an effect. So more generally, with noise-like signals, it's equally immune to any interference. So it seems like a natural choice. So a couple of questions arise here. One question is, how does the transmitter generate a signal having many degrees of freedom that we can guess? And one answer is a pseudo-noise algorithm, an example of which are 1,000 digits of pi, okay, which is shown right here. This is an example of a pseudo-noise algorithm that could be employed. So the second question then is, what's the effect of interstellar propagation on broadband signals? If you're at the receiver, you really can't estimate or compensate for this. But what we can do is model it, and using the model have some idea of what we can do at the receiver with digital signals processing to somehow disentangle or lessen the effects that the interstellar medium is imposing on the signal. So the interstellar medium, so I'm going to talk about this for a minute because I like it. It's pretty cool. So if you take an optical telescope and you look out into space, you see stars and stuff like that. But there's lots of other stuff going on out there that's really cool that you can't see with visible light necessarily. So the first thing here, the interstellar medium is divided into components, has different temperatures and different densities. State of hydrogen is different. And the way that we look at these different structures varies. Okay, so the first component they talk about here are molecular clouds, and there are all kinds of molecular clouds in the ISM. Giant molecular clouds, diffuse clouds, high latitude clouds, cold dark clouds with really neat chemistry going on inside of them. So that's part of what's going. Usually you identify these in the radio and infrared from molecular emission and absorption lines. The next component of the interstellar medium is the cold neutral medium. It's neutral atomic. You can see that with the H1 21 centimeter line in absorption. The warm neutral medium, you can see it, the 21 centimeter line in emission. The two components of the interstellar medium that are of interest to us in terms of having a plasma that will actually affect a signal are the warm ionized region medium and the H2 regions. So as you see over here, interestingly enough, it's ionized, and they detect it with H alpha emission as well as pulsar dispersion. So it's very important that they put pulsar dispersion up there because that's one of the techniques that we're using, and some of the research that our stuff is based on is pulsar dispersion. This coronal gas is too hot to worry about. So how have we learned anything about the interstellar medium? Well, I should have corrected that 4 decades. I think it's actually been longer. But on the shoulders of pulsar studies, there are pulsar researchers like Don Backer, Jim Cordes, Joe Lazio, Lee and Joe Kaipi, Barney Rickett, William Coles, the list goes on and on. Frank Drake has done some as well. Have built this whole database of literature, theory, and different ways to interpret the interstellar medium and their effects on pulsar signals. So they've defined and characterized signal-altering effects of the ionized interstellar medium. And so what we're actually looking at is the interaction of radio frequency radiation with electron density fluctuations in a turbulent plasma. So you have radiation moving in, you have a turbulent plasma, and the effects that occur are typically dispersion and scattering. So those are the 2 effects that we're going to look at. I don't know why some of my titles didn't show up. Anyway, so talking about dispersion, as radiation moves into a plasma, it ends up with a group velocity as it's moving through this ionized interstellar medium. And as you see here, there's a component of the plasma frequency involved because the plasma obviously does have a frequency, and it's usually less, much less than the frequency of the radiation that's interacting with it. So the observable that we have with dispersion is basically a frequency-dependent time delay. That's what we see. That's what we have to deal with. And so what you end up having is a propagation delay. This term at the end there, the integral over the electron density along the line of sight, is the dispersion measure. And that's basically the electron column density along the line of sight. That's been well characterized by pulsar researchers along many, many lines of sight. These 2 diagrams here are from Cordes and Lazio, 2003 or 2006, depending on where you look, show these different studies and some of the results of them. It's really quite intriguing. So we have dispersion measure on this axis in parsecs per centimeter cubed versus galactic longitude. What you see here are pulsars. Solid and circles depict different telescopes that took the data. And as you can see, we get a dispersion measure that goes up a little below 2,000. Of course, the galactic center is going to be very, very high. We're not getting pulsar detections above here because of extreme scattering, pulse smearing, and things like that are going on there. But you can get an idea versus galactic longitude what the dispersion measure is on many lines of sight. On this diagram here, the sun is here, the galactic center is here, and each contour represents a different dispersion measure, this one specifically being 100 parsecs per centimeter cube and this one being 4,000. So interestingly, there are a number of lines of sight that we have dispersion measures for, so it might be, an interesting idea to look along lines of sight that have low dispersion measure, That way we can minimize the effects of dispersion during our searches. Okay, so a much more complex phenomenon is scattering. The framework behind this is very complex and convoluted at times, but I'm trying to simplify it as much as I can here today. So with scattering, you have weak and strong scattering. There are a couple of different regimes, one being refractive and one being diffractive. And in terms of weak, the diffractive and refractive scales as such are indistinguishable, but when the scattering becomes strong, the diffractive and the refractive scales kind of separate out, so you can tell each of them separately. So the way I like to look at weak and strong is in weak scattering, you may have a less turbulent plasma or less of a plasma between you and the wave. So as the wave is coming in, along the line of sight, you get less of the wave deviated. So they're scattered, components are deviated, but you have a lot of the wave that's undeviated. That's considered weak scattering. With strong scattering, most of the wavefront is deviated. So all the scattered components begin to interfere constructively and destructively and can really wreak havoc on the spectrum ultimately. So that's how those two scales are defined in my mind. The Fresnel scale that we use is the typical scale by which to measure everything in scattering. It's about a square root of pi larger than the first Fresnel zone in your normal diffraction theory, if you remember that. So in terms of weak and strong, when I say the diffractive and refractive are indistinguishable, both scales, and I'll talk about these scales in a minute, approach the Fresnel scale in weak scattering. In strong scattering, you have very distinct scales that are related to the Fresnel scale but are scaled differently. So when I talk about strength of scattering, there's a parameter. I visited with Barney Rickett and Bill Coles back at the end of February, and we discussed some of these issues. The strength of scattering that they use is called MB squared. It has a number of components. These we won't worry about, but it's a function of the electron radius, the wavelength, something called the scattering measure, and then a form of the Fresnel scale. So scattering measure is another interesting component because they've done the same kind of measurements they've done for dispersion measure for scattering measure. So we also have scattering measure along many lines of sight. We can also look in those directions that have less scattering. So what the scattering measure is basically is a measure of Cn squared over the path length. Cn squared is actually a measure of turbulence. So in our local neighborhood, I guess within 100 parsecs, it's about 10 to the minus 3.5 meters to the minus 20, kiloparsec meter to the minus 23rds. Very strange units, not fun to work with. But you can approximate this as a turbulence times the distance, and that's a scattering measure. So that's how we determine strength of scattering. Usually it's said that MB squared less than 1 is weak, and MB squared greater than 1 is strong. But we use in the simulations, which I'll talk about, up to 10. So it just depends. So just to talk about these two scales so that it'll make more sense, in terms of scale, distance scale, we're talking about transverse distance through the plasma. So that translates to a distance on the ground, basically. So you run a simulation, you do a scaling for distance, and you can figure out what those distance scales are. There are also calculations for pulsars that you can use to determine those scales. So the diffractive scale is typically when the scattering is strong, less than the Fresnel scale. And that's on the order 10 to the 7, 10 to the 8 meters. The refractive scale is larger than the Fresnel scale and is on the order 10 to 11, 10 to the 12 meters. The Fresnel scale is usually a little over 10 to the 8 meters, depending. You also have time scales associated with these. You can see diffraction on seconds to hours, while refraction is usually days to months. So if you're taking 90-second observations of sources for extraterrestrials, diffraction is probably going to be the more important phenomena to look at. Okay? If you're looking over days or months, then refraction may come into play. But in my opinion, diffraction is the one to look for. You also get intensity scintillations, which is the fading and sort of like a focusing and defocusing of the intensity. And I'll show some of that here shortly. And it's shorter, obviously, for diffractive scales and longer for refractive scales. The long-term intensity scintillations are basically, pretty radical focusing and defocusing. Short-term intensity scintillations are about 100 seconds within a bandwidth of 1 megahertz. So the Fresnel scale down here, I'm just showing that it's actually related. The Fresnel scale squared is related to both the other two scales, the diffractive and refractive. Okay, so there are observable effects from scattering. As I said, for dispersion, it's the propagation delay. You can actually break the scattering effects into diffractive and refractive. So for diffractive effects, we have angular broadening, which is basically just a smearing of the image, all right? It's like a smearing of the brightness distribution of a point source as a function of diffraction. You can have temporal broadening, which is due to the multipath effects, especially at high dispersion measure, and fast intensity scintillations. Refractive effects include angular wander, which over time, a point source can actually be seen to move, in position a little bit. Dispersive and geometric time of arrival variations. In terms of the dispersive time of arrival variations, we're talking about time-dependent dispersion measures. So it's dispersion measures that actually vary in time. And for the geometric time of arrival, it's actually the change in path length. So you get a delay associated with that. And with the refractive effects, you get very slow intensity scintillations. Okay, so in order to understand these effects, we have to model them. So codes have already been produced to model the studies for pulsars. What I've been using is a two-dimensional scattering code to run simulations for broadband signals, and the code was provided by William Coles at UC San Diego. He actually took the code in Fortran and translated it to MATLAB for me. It was really nice, because it would have been a bear to go through all the Fortran. So what's actually happening here is you have an incoming wave, and so what I've done here is made a diagram that kind of talks about the process going on and then what's going on in the model. So you have a signal from an extraterrestrial coming in, and it hits a region of the ionized interstellar medium. We model that as a phase screen. You end up Fourier transforming to get an angular spectrum of plane waves, and you propagate that through space using a Fresnel kernel. And then you inverse Fourier transform this at the receiver to get the electric field of the wave at the plane of the observer. So what I have up here is you have the electric field, and it interacts with the phase screen here. Now the phase screen is basically a Kolmogorov wave spectrum shape, basically. It's a random phase screen that's created. You can change it. You can use the same screen. It's up to you when you're doing your simulations. So you do a Fourier transform to get your angular spectrum. You propagate it to the ground by convolving with the Fresnel kernel, and then you inverse Fourier transform here to get the electric field. So it's actually fairly simple in terms of mathematical operations. It's figuring out all of the details that's a little more complicated. So in terms of modeling, you can change several parameters. Mesh size is important. So in a two-dimensional simulation, you're creating a grid. You can specify the number of samples you want and the sample spacing between them. You can do the same for both x and y. Ultimately, those can be scaled to distance or time. Okay? So depending on what simulation you're running, you can either keep it as a grid or you can scale them to see what you're interested in seeing. You can change your MB squared value to weak or strong. I usually run for a week at 0.3, MB squared at 0.3, strong being 10. For the distances that we would actually be looking, though, scattering strength of 10 is probably out of the question. I would say probably around 3 is maximum for what we might see, and the distances we'll be looking. You can give a number of frequencies. You can give a frequency spacing, and depending on computation time, you can, and what you're looking for, you can vary all these factors. Okay, so one of the interesting things about this model is it really doesn't take frequency into account. You kind of have to put that in yourself. I thought it was odd when I first got the model that it wasn't a parameter you put in immediately because the Fresnel scale is set to 1. So you effectively have to go back, calculate what MB squared would be for the frequency that you want so that the Fresnel scale will be comparable for say 2 frequencies. Say you're looking at 21 centimeter and 2 centimeter or something like that. So you generate a phase screen, and this was actually done at 21 centimeters. And you can see distinct differences between strong and weak. These smaller scale, the scale here, this is intensity. So we're looking at intensity at each grid point here. And the scale is based, you can't even see it, that's horrible, I'm sorry about that. The scale is based on a mean. So the red parts that if you could see in here are at about 22 for the strong. These smaller scale features in here are the diffractive scale, and the larger bunching features are on the refractive scale. Okay. So in the weak case, the maximum intensity here is 4.5, but as you see, your diffractive scales are much less. You get a lot more of the intensity through, in this case here. So obviously this would be a better channel because you're getting more of the intensity of the wave through. You can also create dynamic spectra. And in dynamic spectra, you can see things like drift and other refractive effects, as well as the intensity effects. So what you do to create these dynamic spectra, and these are typically used in pulsar research, is you run this simulation at multiple frequencies. So it makes it a polychromic simulation at that point. Otherwise, each one of these is monochromatic. So you run the simulation at each frequency, you extract the center slice from each of these, and you just pile them up on top of each other. And that's what we've done here. So on this axis, we have frequencies which start at 0 to 128, and that can be scaled by whatever frequency. And on this axis, you can scale it to distance or time. In this particular simulation, the time for the weak scattering, which is this case here, is about 9 days. Run it out for about 9 days. If you really want to see strong refractive effects, you have to run it out for longer. But in the case of what we're doing, we really don't need to do that. We're not going to be looking at a source necessarily for more than, a couple of minutes. Another interesting approach to this was brought up by Lazio and Cordes and Lazio, was revisiting sources because of scintillation. So if you have, and I have all these references if anybody's interested, there's a whole series of papers by Cordes and Lazio and Cordes and Sullivan on scattering and SETI signals, but it's mainly for narrowband stuff. It is for narrowband stuff. So if you have strong scintillation occurring, it might be wise to revisit that source. You don't see something at one time, you might revisit at some point, and you might actually see it. So they actually come up with a timescale that you can go back and revisit the sources. So there are other things you can look at in these simulations, and one is phase. This is phase in radians versus time. And this is the phase of the phase screen, and this is the phase of one of the channels. And as you see, in strong scattering, you get somewhat major phase differences from the phase screen. In weak, it pretty much follows the phase of the phase screen. That makes sense because it wasn't scattered as much. So you don't have as much of the rays deviated as you do in the strong scattering. You can also do other things. You can do a number of other things. With the simulations, you can simulate Doppler. You can look at power and other types of features. But what we want to do for broadband signals is basically look for time and bandwidth coherence. And what I mean by that is looking at points over which the phase is stable. It'll help to narrow down signal design, as well as allow us to search in certain spaces. So it gives us, it gives us freedom. It also gives, narrowing down the design criterion by the extraterrestrials. So in order to do that, one thing I'll do is run several simulations at different spacings. I can get a finer and finer grid to determine, at what point my phase is significantly changed versus time and versus frequency. So that's something that I'll be starting on pretty soon. Another thing that we're going to do is develop a statistical model of the channel. It'll give us an idea of how the channel reacts, and we can implement some of these features at the receiver, hopefully. And then ultimately implement any of the new algorithms we have into the search. So I'm not exactly sure how that's going to go. The Allen telescope array is the obvious choice for doing that. And so in conclusion, I had so much formaldehyde stuff I wanted to talk about, and I didn't think I had time. Anyway, so in conclusion, there are obviously compelling reasons to expand the search to include broadband signals. Modeling can be used to ascertain the effects of the ionized interstellar medium on broadband signals. And continuing work will narrow down the time bandwidth coherence of broadband signals given the ionized interstellar medium impairments. So that's actually all. I should have added my formaldehyde stuff, but anyway, that's all. Thank you.
Thanks for that interesting talk. Jill, do you want to do questions, or do you want me to?
Well, you've got the mic.
First, do you want to just take a minute and tell us about all the interesting formaldehyde stuff?
Yeah, that'd be great, actually.
We'll leave it question.
Okay, so, gee, I should have put all my stuff on there. But so typically, the galactic habitable zone has been defined as this, 7 to 9 kiloparsec annulus around the galactic center. So my professor and I decided, well, hey, what's going on with the outer galaxy? Nobody really looks much out there. It's kind of like left in the dark. So we decided, okay, formaldehyde has been detected out there. Let's do a survey of this. Let's see, what we can find out there. So we took sources that were giant molecular clouds that were identified by IRAS and ultimately mapped in CO by Jan Brandt and Jan Volterloot, who are our collaborators, and took about 70 of these clouds and looked for formaldehyde. Originally, we used the Kitt Peak 12-meter telescope and looked at 140.8 gigahertz. Got detections in a great number of them. Over probably 65% of them we got detections. We took those and also looked at them from Arecibo with the 4.83 gigahertz line. Had detections in several, but we had limited visibility at Arecibo, so I still need to do 4.83 gigahertz observations with hopefully the ATA soon. So that work needs to be continued. And we had some measurements at 225 gigahertz from the JCMT. So I only had one source. This is sad. I only had one source that actually overlapped in 3 transitions. So what's important about that? Well, in order to understand abundances and to get abundances of these molecules in the outer galaxy, you have to run a statistical equilibrium program. So in order to do that, all the energies are put into the program and all the energies in the different levels. And so if you have more than one transition, you have you can have greater confidence in what you're modeling and what values are coming out. So we did the same with HCN, the 88 gigahertz line, using the 12 meter, several detections as well. As far as abundances compared to intergalaxy measurements, 2 to 3 orders of magnitude less in the outer galaxy. So obviously, one thing that would be interesting to look at is where does this abundance really drop off in the outer galaxy? We're finding it out there. And when I'm talking about the outer galaxy, I'm talking about distances over 16 kiloparsecs. So we're looking at 16 kiloparsecs out to about 24. And we're detecting formaldehyde all the way out there. It's definitely out there. So we did the same thing with hydrogen cyanide. And I only got one transition. So I have several transitions left to get for that. Working on getting time at Green Bank to do the 14 gigahertz transition of the formaldehyde line. So ultimately, I'd like to move into a metallicity study just because I don't think metallicity values have been very well established for the outer galaxy. Understanding metallicity will allow us to understand the potential for terrestrial planet formation and kind of move the definition of the galactic habitable zone out a little bit. I'm also interested in looking at these prebiotic molecules in different stages of solar system evolution. So circumstellar disks and different stages moving towards disks with planets, and see what happens to the gas phase formaldehyde as we move through these different structures. So that's pretty much my formaldehyde work, but it was really exciting. And I had all these cool diagrams of the, of the galaxy and all the clouds I had detected it in and not. So that was pretty good. Okay, so now I'm done.
That's great.
Yes.
Any other questions for Samantha?
So I'm still kind of fundamentally confused about one thing here, which is from a SETI search perspective, you're going to be looking for these spread spectrum broadband signals, right? The whole point of doing this modeling is that you want to be able to see how they might have mutated through interstellar space. But the whole point of a well-designed spread spectrum technology is that it is indistinguishable from white noise unless you have the pseudorandom noise code, and in particular even the relatively primitive technologies that we do here on Earth use phase shifting as part of their technology for transmission. So what exactly are you looking for to know that this is a ET signal versus just noise?
I think the ultimate goal would be a matched filter scenario. So you're detecting a signal. You have a matched filter of something you think the signal might be, and then you can use that to pull it out of the noise. Do you want to add to that, Dave, since he's the signal design guy?
I'm the
Communications guy.
As the first slide said here, you really have to know, what the signal is to search for it.
Mm-hmm.
That's kind of a fundamental rule of nature if you're going to get reasonable sensitivity in white noise. But if you do know what the signal is and you can match filter against it or correlate against it, then the only property of the signal that matters is its energy. It doesn't matter its time duration, its bandwidth, exact waveform, etc. None of those things matter. So the assumption is that we know what the signal is, or assume what the signal is, by assuming that ET is using a similar signaling scheme and some sort of pseudo-random generator, which is what we use on Earth in Earthbound systems as well. So then it becomes a matter of us guessing what pseudo-random generator they're using. And there's one fairly obvious choice, and there may be others. A fairly obvious choice is the binary expansion of the irrational number, which turns out to be a wonderful coin toss statistic generator. And has all the right properties for this application, but there may be others. I mean, you can talk to mathematicians about what pseudo-random generators do you think are common in the universe, staying within the realm of simple. And then we probably would do a search over a set of such, prioritize them and do a search over a set of such pseudo-random generators. So basically it comes down to guessing the pseudo-random generator. But you're right, if you don't know or guess the pseudo-random generator, then the signal looks like white noise, so it's basically indistinguishable from the background noise.
So right now, we're searching through frequency space. For the narrowband signals, we have to search over frequency. And there's a very efficient, fast FFT algorithm that lets us do that. You're going to be, in this domain, you're going to be searching over different code generators. And so we're going to have to look for efficiencies. And the best thing to do is to find, there are only a certain number that actually will propagate over long distances and still maintain
So you want
their
to take the initial
coherence.
reading and actually back-figure what the reasonable pseudo-random noise would be to propagate in that environment.
Yes.
Yeah, especially the bandwidth and time duration, which the theory says from interference point of view, you want both those to be as large as possible. But then the characteristics of the interstellar medium then limit how large those can be. So that gives us a nice clue as to where to look. That ET will want to make both the time duration and the bandwidth as large as they can without running into incoherence in time and frequency. So that really significantly narrows down where to look. That's a really nice feature. So this is a case where these impairments in the ISM scattering and so on are actually helpful to us in terms of coordinating between ourselves and ET.
I think you didn't show, when you were listing effects for the diffractive scattering case, you didn't show any time of arrival effects. Is that just because they're too small, or are they even smaller than an extrapolation from the strong case?
I actually haven't, for the signals that we're looking for, I haven't measured that yet. But time arrival variations, let's see, I've actually got a, it depends. So,
Well, what I'm really interested in, is there any wavelength dependence of the time of arrival in either case, I guess, the diffractive or...
well, definitely with the dispersive, because you're dealing once again with dispersion. You're dealing with time variations in the dispersion measure due to time variations in the electron density fluctuations. So the other one is geometrical. So that's actually just a geometrical optics problem, which is what I would say is not so wavelength dependent. So.
Thanks.
About SETI signals, having to guess to match filter with a single signal would imply that they're trying to signal you. But if they're actually trying to communicate, wouldn't it be better to try and look at the distribution of the signals themselves? In other words, instead of matching each signal, collect signals and match them. In other words, I think communication could be picked out by looking at distributions of signals as opposed to just matching single signals. And it's basically signaling versus communicating.
That's another communications question. So
Yeah, absolutely. Yeah, I'm an astrobiologist. I can't answer these things.
from a communication engineering point of view, I would expect that they wouldn't be transmitting a separate signal for acquisition from communicating actual data. Because on Earth, last time we did that was about in 1825. So it turns out to be unnecessary and kind of wasteful of power. If they're power constrained, then we wouldn't expect from a communication point of view. I don't know anything about alien psychology, but from a communications point of view, I wouldn't expect them to do anything special for acquisition, because there's really no need to. So the kinds of signal we're talking about here is just the waveform that would be used to communicate one or some small number of bits of information. And that waveform that we've been looking for would be something like phase modulated, or more likely orthogonal modulation, where they would actually, say they transmitted a signal based on pi and another signal based on the square root of 2, both of which are great random number generators, then that would communicate one bit of information. And it also would be consistent with efficient acquisition, because when we correlated with pi, we'd see the signal part of the time. When we correlated with square root of 2, we'd see the signal the other part of the time. And we wouldn't lose anything with respect to acquisition. So given the phase incoherence of the carrier part of this transmission, you're talking about a very long distance of propagation and very kind of unstable channel from a phase point of view. I don't think the kind of coherent modulation schemes that we use here on Earth, like quadrature amplitude modulation, are in the cards. But a modulation scheme which is quite consistent with this channel would be an orthogonal modulation. And that's somewhat inefficient from a bandwidth point of view, but again, bandwidth is free, except for these dispersive effects that we have to worry about. Otherwise, bandwidth is free, unless there's some interstellar internet out there that we don't know about that we would be interfering with. So that would be good news. So I think that everything we've said here is quite consistent with a signal which is used primarily for communication, and we're just talking about the acquisition part of the problem. Once we've acquired a signal, then of course we record it and analyze it up to the kazoo, and then we kind of deconstruct what modulation scheme is being used and then ultimately what the information or message is.
So one of the great benefits of using the spread spectrum, of course, is the coding gain that you get, which is based primarily on the length of the code. As I understand the presentation, the longer observations would be more subject to these effects of diffraction and refraction. So reasonably, what kinds of coding gains are you expecting to get? What kind of code lengths are you expecting to look for? I'd imagine that if you're talking many days at a time, that's quite a huge gain.
Communications question.
Let me take a communications course.
Sorry to
Yeah.
steal your thunder.
No, I'm glad you're here.
Yeah, the processing gain, which is the extent to which interference is uniformly suppressed through the match filter process, which was mentioned here, is proportional to the time bandwidth product. So ET would want to make the signal as long as possible and as wide a bandwidth as possible in order to suppress interference at the receiver end. If they were empathetic to our interference issues, and the hypothesis is that they have even much worse interference because they're probably a more mature civilization. So they probably are arguably quite motivated by helping us to detect in the presence of interference. More interestingly, in the detection of presence of noise tells you nothing about the signal to look for. In interference tells you a lot about the signal to look for. So it's a really nice way of coordinating between transmitter and receiver without explicit coordination. But so the answer is they would make both the time duration and the bandwidth as large as they could. What limits them? The effects that Samantha's talking about. So that's another nice feature of the fact that we have these impairments is actually somewhat fortunate because it tells us a lot about where to look in terms of time duration and bandwidth for signals. In terms of specific numbers, I don't think Samantha's gotten far enough to be able to tell you. What we would like is time bandwidth products on the order of, say, 1 million, 10 million, something like that, which then gives you on the order of 60 to 80 dB suppression of interference. Would be nice. Will the channel support that? We don't know yet.
You're not piping up about beacons, but suppose there is another timescale that has not to do with the interstellar medium, but the thought that perhaps what you're seeing is not something that's continuously broadcast at you, but in fact is broadcast sequentially. You're on somebody's ping list, right? And so the time that is of interest is how long they're going to continue putting information in your direction before moving to another direction. So as you know, we've already thought the easy thought. The circularly polarized sine wave goes through the interstellar medium unperturbed, and we're doing a good job at looking at that. The rest is a lot to try and work through. We haven't ever been able to find magic times. Some people have thought up magic frequencies, but magic times in terms of this transmit-receive, we haven't come up with them.
Lawrence
We should let
has a-
Samantha answer a question.
Oh, Lawrence has a question in the back.
I wanted to ask about the outer galaxy. Is that the extended disk, or is that the halo, or you were referring to molecular clouds and so on?
The B values are 2 to 3. So, I mean, it's along the disk as well as a little above and below. So, I mean, these are giant molecular clouds. So there's actually an outer arm out there. And we think we're tracing it with these clouds. So if I should have put my stuff in, I could have shown you where it is. But yeah, so there's still a lot of material out there, and it's kind of interesting. I mean, where does the molecular abundance really drop off? You know, I mean, you've got all that H1 out there ultimately, but where are the molecules dropping off? That's, you know, dropping off radically. So still gonna, you know, keep looking at that.
What other molecules?
What other molecules?
Yeah.
you know, as the abundances get lower, it's really hard to detect some of the molecules that I'm interested in looking for. I mean, anything that has phosphorus in it, any of the micronutrients, the things that life would need, I'm really interested in looking for. Phosphorus, magnesium, potassium, nitrogen. Nitrogen's another one. In the outer galaxy, nitrogen is ammonia. I don't know if they've detected it, or if they have, it's been really low in abundance. So what's the deal with nitrogen out there is another question, you know, that I'd like to look at. So,
what about amino acids? Just
not me, you know, maybe Lou Snyder and those guys, and, you know, but in terms of me looking for those, no, I'm not. I want to find the precursors. They're easier to find and easier to disentangle the spectra. So.
Is there an upper bound on bandwidth? So, in which case, what's the physics? Why would there be an upper bound on it at all?
Well, at some point, you're not going to have phase coherence. So if you're looking at, you know, this thing is getting caught up. So if you're looking at magnitude and phase, at some point you're not going to have phase coherence. So at that point, going beyond that is useless. You're not going to be able to detect anything. So that's why we're trying to, you know, figure out where the sweet spot is in that in terms of search space by looking at phase. So.
Do we have other questions?
Yeah, just one question. I mean, the last time I paid attention to this, I'm out of date. I mean, it's clearly everybody believes the three-phase model for the ISM. And the last I paid attention, we didn't really understand what the structure was, whether we had tunnels or holes or... what I was wondering is when you construct your phase screen, how robust is that? I mean, you've got to put in, because your dispersion and your scattering are both integrals over line of sight, and you're using a Kolmogorov spectrum. Can you comment on how robust your phase screen is to your suppositions about the turbulent structure of the ISM?
Well, that's a very good question. So the way they generally model the phase screen is a thin screen. They've done several different studies, thick screen, thin screen, propagation between screens. What Barney Rickett told me, because I asked him about this, about the structure, he says they kind of model it now as these clumps. So the thin screen basically represents one clump.
Right, you're interested in 10 to the 8 meters or so.
Mm-hmm.
Okay.
So that's basically the way this model works. There are other models that actually do propagate it between screens. If I find that it's necessary to do that, I'll set that up in this model as well, you know. But that's the way Cole's model works. So.
Cool. Actually, I had one comment. You said you didn't understand alien psychology. Maybe you should ask Stephen Hawking. He understands it.
I think he's just making a worst case assumption.
That's great. Let's thank our speaker.